Good morning, everybody. My name is Jenkins. I'm a second-year physics major here at UCSB, but this summer I've been working in Sanji Han's physical chemistry lab in the Department of Chemistry, working on a new apparatus for double magnetic resonance experiments. So, something I'm sure you're all very familiar with is magnetic resonance imaging, or MRI. This is something that was revolutionary to the medical field. Its invention no longer required invasive surgery to look inside of somebody to diagnose diseases or see if something is wrong. We can get a cross-sectional image of somebody. But other than laying somebody down and sticking them in a magnet, how does magnetic resonance imaging work? It works on the principle of nuclear magnetic resonance, and this is useful in chemistry for NMR spectroscopy. With one simple set of analytical tests, we can determine structure of molecules, properties of materials, and even dynamics of molecular systems. So now I'd like to talk to you about the background of NMR and kind of how it works. So here we have a nucleus, and if it inputs some kind of electromagnetic radiation, it can take it to a high energy state, and when it relaxes back to the lower energy state, it emits this electromagnetic radiation. But something that's essential to this is that we need nuclei with spin. So you might ask yourself, what does it mean to have spin? For our purposes in NMR, it means that it has an unbalance of protons and neutrons in the nucleus. So an example of this is carbon-13. It has 6 protons and 7 neutrons, and this gives it the intrinsic property of spin. And something that's very important is that things with spin act like little magnets. So if we put a bunch of them in a magnetic field, almost all of them will align with this magnetic field, giving this magnetic moment vector. And if we pulse perpendicular to this magnetic field, we can knock our spins down perpendicular in the plane perpendicular to it. And when we turn off this second magnetic pulse, they'll process around. And this is where we can detect our signal. When the spins are pointing at us, we get positive signal, and then 0 and negative and 0 again. And if we graph this signal versus time, it looks like a sine wave. And we can Fourier transform this to get these sinc functions that tell us the structure of this molecule. So this is ethanol, something that's pretty common in iota stuff. All these peaks of signal represent where protons are in the molecule. So NMR is something that's been around for a long time. It was discovered in 1938. So what we're looking at here is kind of like a new approach, is dynamic nuclear polarization. So this blue moment that we discussed earlier, it's important to realize this comes from a polarization of spins. So when we turn on our B0 magnetic field, there are 2 distinct energy levels that the spins can be in. They can align with the magnetic field, which is the lower energy state, or they can oppose it. And this is most of them will be in the lower energy state. And since spins can interact with each other, because they're like little magnets, if you put 2 magnets next to each other, they feel a force between them. You can transfer spin polarization from one species to another. And using this, with the fact that electrons are very easily polarized with microwaves, 600 times easier to polarize the nuclei, we can transfer electron spins to other nuclei. And the new thing that we're trying to do is transfer the electron spins to protons and then to carbon-13 in our sample. And our instrumentation isn't developed yet to do this, but previous DNP experiments have shown that when you do polarize your electron spins and transfer them to your nuclei, there's a drastic increase in signal, possibly orders of magnitude larger. So our new method for doing this is we have some kind of unknown surface, most likely a polymer or something that just contains carbon and proton, and we submerge it in a radical solution. This means it's some kind of proton-containing molecule that also has a free electron on it. And if we irradiate our sample with microwaves, this polarizes our electron spin, and the electron spins interact with the proton spins, and it polarizes them as well. And then if we run pulses through an inductor, we can transfer this proton spin to protons and carbons in the surface and get information about the surface. This like the structure of it or the properties of it and like how the radical solution is interacting with the surface. But to do this, we need a new kind of specially designed probe that you can't buy commercially. So we have to design it to have two channels, a proton channel that will make a pulse through this inductor at protons, resonance frequency, and a carbon channel. And this will give us this DNP and cross-polarization capabilities. And it's also been designed to be easily interchangeable with the coils, so we can do a bunch of different nuclei, as well as like proton and carbon-13. And our experiments have been constructed so that we get very high resolution, or very like, narrow peaks that you saw earlier, so it's very well distinguishable, as well as high detectable signal, so we can get a lot of signal. And with that, I'd like to thank you all for coming and open it to any questions. I'd also like to thank the Gorman Scholar Program and my PI. Are there any questions?
I have a question. I didn't quite get this piece. What's a transfer spin polarization again?
Oh, okay. So things with spin are like little magnets, right? So if you could imagine taking two magnets and putting them close to each other, they feel a force, right? So that's exactly the same thing that happens with spins. So when you have like a lot of spin ups, they can bump into other like spins and flip their spins as well.
So then all the spins are in that direction? Or?
Almost all of them will be in that direction. So when you're just irradiating your sample with microwaves, you're only polarizing your electron spins. And they're like in the solution, and there's protons in the solution, and they bump into them and they flip the proton spins as well. Instead of having equal or almost equal amount of up and down spins, you get more up spins than down spins.
Okay.
Yeah. Yes.
So I'm kind of curious about what kinds of samples you'll be able to analyze using this method. You mentioned it has to be some kind of surface. Does that imply that the sample needs to have some sort of property where it can be nicely polished down, or is it just important in that it can only measure near the surface, or does it measure the bulk of the sample as well?
Really the only constraint on doing it with this method is that it contains carbon and protons. Other methods of going straight from electrons to the nuclei that you're trying to measure, you need kind of a porous material where the electron can get in there, but that can contaminate your sample sometimes, which is why we're not going straight from electrons to the nuclei that we're doing. But really, like, you can do it on like diamonds or any kind of like polymer. Yes.
So NMR is widely known and used in chemistry. I'm still confused on the concept of double NMR and how it will impact the chemistry community.
It's mainly an instrumentation thing. Double resonance, you detect more where the carbons are close to the protons, so more of like the bonds. As I showed the ethanol spectrum, that's only showing you where protons are really. So you can kind of like intuitively find the structure from looking at that. But this looks at more of like where carbons are close to protons. And how this is useful in chemistry is you can take an unknown polymer or anything that you want to like find the structure or make sure you have the right material, and with like one simple set of tests you can like determine the structure of the molecules that make up that polymer.
So there's no size limit on this instrumentation?
If you have enough power, there's not a size limitation. What we work with is mainly like 6 millimeter samples. It's pretty small, but if you had a huge magnet that was like, I don't know, like 14 Tesla or something, you could probably use bigger things. But we try to keep it smaller for power reasons. Yeah.
Is there any other group doing similar work or trying to come up with techniques that also will help you analyze these more solid state compounds?
Yes, there are other techniques in our lab that we use, and there are some other chemistry groups that do it. One of them is called magic angle spin. I know it sounds a little ridiculous, but it has to do with the Hamiltonian, or the energy operator for our system. There's a 1 minus 3 cosine squared theta term in the expansion for it, and if you solve that equals to 0, there's a 57.74 degree angle or something, and it turns out that if you spin your sample at that angle around the resonance frequency, then you get like super narrow lines, and you can do it on solids or solutions or anything like that. It's complicated. There's some like quantum mechanics that need explaining.
So if you have a solid that has impurities in it, are you going to be able to characterize it?
Yeah, you can find the location of the impurities with this radical solution. There's an electron like in the molecule that can like go and get in like the pores of the material, or like attach to the material, and it'll show you where that is in your sample. Like if it has that impurity in it, you'll get a signal out. But if there's not the impurity that the electron can attach onto, then like you wouldn't get any.
So you can also measure how pure your sample is?
Yes.